Folks, we're going to do something called the first derivative test. But I want to remind you what happened just a little while ago. We looked at finding all the extreme values on an interval. Hey, how do we find those extreme on an interval from A to B? We took the critical values. Those are the values where the derivative equals 0 or is undefined. And then we evaluated the function value or the y-coordinates of each and every one of those critical points. And we did the same at the endpoints. And when I had the critical points and the endpoints, I knew I had to have the highest and lowest points there. But when we don't have this on an interval, there are no endpoints. And there's no comparison that needs to be done. We have a few other rules, but essentially you do the same thing. You're going to find the critical values. And then, this is some big stuff. There's only 2 steps here other than finding the critical values. But this one is really important. It's not hard. It's just understanding it the first few times. And then part 3, I really say use common sense, but I find that that common sense is usually fairly uncommon among the general populace. So I'm going to ask you to engage your brains, come up with a thoughtful answer, and do something that is unusual in our times. Think. So, first things first, I have a function up here. I want to find all the extreme values. Let's just take the derivative. Well enough, we have a derivative. Sorry that there is a light shining through the 4x cubed. Some of these things cannot be helped. Secondly, I want to find out anywhere where this derivative equals 0 or it's undefined. Clearly, there's nothing here that's going to make this polynomial undefined. Nothing's going to be divided by 0. There's no asymptotes, no breaks, or anything like that. But we can find out where it equals 0. And so we see that when x is either positive 1, negative 1, or 0, this derivative will equal 0. So now here's what I mean by a sign chart, and these critical values make the boundaries. I'm going to look at every number on this entire graph from negative infinity to infinity. And I already know that 3 of those numbers equal 0. Now, if there's only 3 numbers that equal 0, that means every other point on this graph will be either a positive number or a negative number. Since this graph is continuous on those intervals, if one number in this interval is positive, every single number is positive. If one number in this interval is negative, then every single number in there will be negative. So all I need to do is come up with a little test case. Maybe I'll pick out the number negative 10, which is in that first interval. Plug negative 10 into your derivative and determine whether it is positive or negative. And then I want you to do the same for each of the other intervals. Now, I showed you what my test number was, but you could have used anything between negative 1 and 0. Don't use negative 1, don't use 0. Pick any number in the world between there, though. Plug it into your derivative and find out, is it positive or negative? I don't care what the number is. So sometimes using a bigger value, I plug 10 in and realize, hey, that's 4,000 minus something. Great. I'm stopping there. I know that's going to be a positive number. Also, these will not always alternate. They often do, but not always. And here's what this means. I was plugging these in my derivative. That means when I look at a negative number, my graph must be decreasing there. When I look at positive numbers, I know the slope or the derivative will be increasing. When I look at all those intervals that are increasing and decreasing, I bet you can figure out where are my maximums going to be and where are the minimums. Hopefully this is where the common sense kicks in. If I have a graph that's decreasing, 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 and then suddenly starts increasing again, guess what that point is going to be? Hopefully a minimum. If I have a graph that's increasing, increasing all the way up to 0, and then starts decreasing at 0 and going down again, hopefully you realize that would have to be a maximum. Now this is very important. We plug these values into the derivative to find if they were increasing or decreasing. Where do we plug in the values to find the actual points? Hopefully you said, to get the actual y-coordinates or the y values, go back to your original equation, which gives you the height, the function value, the y-coordinate, whatever you want to call it, and you'll find the actual points. I filled in the y coordinates now by plugging them up top.